Welcome to Statics.
Example: particle equilibrium. In this example, we'll work a two-dimensional equilibrium problem. We're given a mass of 10 kilograms that is supported at point A by two chords, chord AC and chord AB. Chord AC is horizontal and chord AB is inclined at an angle of 30 degrees from the horizontal axis. We are asked to find the tension in AB and the tension in AC. To begin, we'll draw a free body diagram of particle A. Notice that we have tension in chords AB and AC, and we also have the mass. We need to convert the mass to a weight, which is a force. We can do this by multiplying the mass in kilograms by our gravitational constant in SI units, 9.81 meters per second squared. This will give us units of newtons. Often, in simple problems like this, I will do that directly in the free body diagram. It's important that we make an assumption on direction when we are placing the forces for cables AB and AC. Typically, I will assume tension as I work the problem, and if I get a negative answer for either of the tensions, I'll know that my assumption was incorrect and that the arrow should have gone in the opposite direction. Furthermore, it's important to note that a chord can only support tension. So if I end up getting a negative value, I will really want to evaluate my work. With my free body diagram complete, I'm now ready to apply my equations of equilibrium. I have two choices. I can sum forces in the x direction or in the y direction. Typically, you'll need to use both of these equations of equilibrium to solve a problem. Before I jump in, it is a good strategy to analyze the problem to see if I can write an equation with just a single unknown. Doing so will simplify my work. Engineers are efficient, and I'm trying to be a good engineer. Let's analyze it. If I sum forces in the x direction, that's horizontal, I will get components from both TAB and TAC. These are both unknown, so the equation will have two unknowns. However, if I sum forces in the y direction, I will have the weight and the y direction components of TAB. TAB would be my only unknown. So let's expand our equilibrium equation in the y direction first. I will use the typical convention of components pointing upward to be positive and components pointing downward to be negative. In the positive y direction, I'll have the y component of force TAB, which is TAB times the sine of 30, and in the negative y direction, I'll have my mass times gravity. I can rewrite the equation to solve for TAB. I get that it is 196 newtons. With the solution for TAB known, finding TAC will be easier now. Summing forces in the x direction, I will use the typical convention of components pointing to the right are positive and components pointing to the left are negative. I'll take TAB, which is 196 newtons, and multiply it by the cosine of 30, then subtract TAC. Solving for TAC, I get 170 newtons. I clarify my answers, and I am done.